Fingers crossed that it still comes up. All right, sweet. Great. All right. So hello, everybody. Start the presentation here. So welcome to my talk on self-hosted Kubernetes and Bootkube. My name is Josh Rosso. I work for a company called CoreOS. I'm part of the services engineering group. We're an extension of the core engineering group where we both work on code, but also go out with customers and help them set up infrastructure, Kubernetes, all that good stuff. So it's a lot of fun. And yeah, I'm really excited to talk to you guys. I actually came to the first Kubernetes meetup, the last one on COPS. Show of hands, who is there? A couple of you? Awesome. So yeah, and I actually didn't even realize Boulder had such a big Kubernetes community, which was cool to see. And seeing all the awesome COPS work, and thanks Deis for putting this on. Really, really psyched to see that there's such a big community around this stuff. So quick poll of the room. Who's heard of CoreOS in some capacity? Fantastic. Okay, great. So this will be quick. We do a bunch of stuff in the open source world and in the enterprise world as well. We are probably most known by a lot of you by etcd, effectively the data store inside of Kubernetes. We work on that quite a bit. We also have Container Linux, or as you might have heard it called CoreOS Linux in the past, an operating system that's been rethought on what Linux would look like if it was based on running containers. Rocket, our container runtime engine. Claire, a security vulnerability tool for scanning and seeing what vulnerabilities are in your container images. Flannel, an overlay network. And then finally, Tectonic, which is our kind of enterprise Kubernetes setup. So we use pure upstream Kubernetes. We don't like fork it and keep different flavors or anything like that. But we do build a lot of like enterprise tooling around it, like RBAC stuff that syncs into SSO and LDAP and things of that nature. The stuff that I'm going to show you today is all open source. It's something that you can bootstrap and get set up, but it's actually the piece that we use behind the scenes with Tectonic as well. So I'll kind of show a little bit of that, but again, all the stuff you're going to learn today is stuff that we're pushing upstream and trying to get some feedback on and ideas around the implementation of regarding self-hosted Kubernetes. So my topics will be Kubernetes control plane. We're just going to do a quick review of what the Kubernetes control plane is, make sure we're all baselined. We'll talk about self-hosted Kubernetes and then bootstrapping self-hosted Kubernetes. And I've got some of this stuff set up, so I'll just kind of conceptually talk about it, show you all, maybe field some questions if need be as well. So next poll of the room, show of hands, who's using Kubernetes in production to some degree? Okay, who's more in that stage where like you're kind of learning about Kubernetes, or maybe you've got it in like a dev environment and you're playing around with it and all that good stuff? Okay, cool. So we're about 50-50 split. Sweet. So let's just quickly review Kubernetes architecture. I made this last night with two objectives: to use the most obnoxious colors I could find, and also to leave things out to keep it somewhat simple, just so we can focus on stuff. So if you look in here and you're like, Josh, you didn't put the kube proxy in there, that was intentional, just to kind of outline primarily that left side, which is the control plane, okay? So those of you a little bit fresher to Kubernetes, some of the key things to keep in mind with Kubernetes is while Kubernetes is really awesome for orchestrating our apps and making our kind of nodes look like this distributed compute that can potentially expand and contrast, we do have some components in Kubernetes we need to instantiate or set up to make all of this awesomeness work, right? In particular, we need an API server that we and all of our nodes talk to. We need a controller manager that can ensure certain things stay the way they should be. So most of you know the controller manager probably from replica sets, right? You express that you want two instances of a pod running, and the controller manager, or specifically the replication controller, if you will make sure that those two are running. We need a scheduler that can make informed decisions. So when you express, here's my desired state of the world, the scheduler can say, okay, well, based on that, I need to put this pod here, and this pod here, and this pod here, making those scheduling decisions. And then lastly, etcd, the data store. So all these three components that you see inside of here are all stateless, and etcd is the one where the state is being stored in. And etcd's focus, of course, is performance and high availability. Now, on the worker plane, as I've named it here, we effectively have our nodes that we're going to have our kubelet agents in that are going to talk to the API server. These guys are going to go in and actually communicate and say, you know, what work do I need to have done? Kind of keeping an eye on what they need to be doing on each node. Inside of the nodes where the kubelets are running, we're going to be actually running our pods. And just a reminder, pods can be effectively multiple containers or a single container, depending on how you've got them set up, okay? So most of this we're pretty familiar with as far as the architecture itself goes. Let's talk about what this looks like from self-hosted Kubernetes. So again, on the left side here and the right side, a lot of the benefits of Kubernetes come on when you think about this notion of having these kubelets that are aware of the world and what Kubernetes' desired state is and so on. So with self-hosted Kubernetes, I'm going to take you through a couple things. First, I'm going to show you what self-hosted Kubernetes is, then walk you through why we think self-hosted Kubernetes is a good model, and then show you how we achieve self-hosted Kubernetes. So a little bit harder to see, but this is effectively what self-hosted Kubernetes is. And I don't have to spend a whole lot of time describing this because the bottom piece is really all the same. You still have your worker nodes, they still schedule apps. But what we're kind of rethinking with self-hosted Kubernetes is, what if we could have Kubernetes actually manage the control plane itself? So we have the API server, the scheduler, the controller manager. What if these could be deployments inside of Kubernetes itself? And we could have dedicated control nodes and effectively have these scheduled on the control nodes. So what you're looking at here is effectively what an HA control plane would look like in a self-hosted Kubernetes model. The green squares, or kind of squares, rectangles you see here, are the active ones. So in a HA environment, the API servers are all going to be active because they can sit behind a load balancer. They're stateless. Requests can come into them. The scheduler are going to be kind of on an active-passive model. So one scheduler, in this case the one in the middle, will be elected as the leader, the one making the scheduling decisions. And these guys will just hang out and say, hey, scheduler, if you die, I'll try to elect myself and take over from there. And then same goes for the controller manager at the bottom. Okay, and I'll show you some of that in the HA sense in a demo in just a sec. But really the premise, just to kind of give you a baseline, is taking the API server, the scheduler, the controller manager, and deploying it just like you do any other piece of your Kubernetes cluster. Okay? So, again, what is self-hosted Kubernetes? Having Kubernetes manage its own components and effectively making these core components native API objects inside of Kubernetes. All right? So let me just give you a quick visual of what exactly this looks like. All right? So inside of my Kubernetes cluster, do a quick clear here. Okay? So inside of here, if I were to come in and say kubectl, let's see if I've actually got this in here. Get, yeah, there we go. So I'm going to say get daemon sets, deployments, and configuration maps for a namespace in Kubernetes called the kube system. Okay? And if we look inside of this cluster here, bear with me as I get my zooms right so you all can see this a bit easier. There we go. All right, so you can see inside of here that when you're looking at a Kubernetes self-hosted cluster, effectively the API server itself is a daemon set. We're running Flannel in this case as a daemon set. And if we wanted to plug in Calico to do like network enforcement and stuff like that, we could plug that in as a daemon set as well. The controller manager, the kube scheduler, these are hosted as deployments, just like you deploy your apps inside of the cluster itself. So we have visibility into what our kube system is from a log standpoint, from a configuration standpoint, all through the same manifests and configurations we're used to using for our normal applications inside of Kubernetes. Okay? So we've got these main components hosted inside of here, and I'm going to double click on each of them shortly to give you a better sense of how exactly this works behind the scenes. Before I do, does this make sense so far? Do I have any thoughts or questions on what this is? Yeah, please. Yeah, great question. So I'll talk a little bit about Bootkube, the project, in a moment. Right now, we've got this whole model built into kubeadm, and we're working on putting it in a couple other tools as well to allow for this to, ideally, if we have it our way, ideally this would be kind of the premier choice of how you run Kubernetes. So the tooling you use would support the ability to run it as self-hosted, if you will. Yes, please.
A beginner question. Your control plane in the traditional way it's been done.
Yes.
Is that running in, say, like CoreOS, Linux?
Yeah, great.
Single instance, or I suppose multiple instances for high availability?
Great question. So as far as going back in time and seeing how these would be run, or not back in time, but the present day of how most of these are run, typically your API server, controller manager, scheduler would run on hosts in containers. Some people use systemd units to bootstrap them. As far as high availability goes, totally. Most production Kubernetes clusters are going to have these highly available, which means replication of all three of these components and etcd, the data store as well. You got it. Yeah, and there's a lot of different ways that you can approach it, but think of these as hosted outside of the cluster through some means and managed through some other means, like a Docker container or something like that. Yeah, great question. Yeah, as you'll see, the communication model is quite similar, but the big difference, as you'll see, is these are actually living in the cluster. That brings a lot of benefits, but also a couple concerns as well, which I'll bring up very soon. Great questions. Okay, so continuing on here. So we've got this idea of self-hosted Kubernetes where we are running Kubernetes inside of itself. So why would we even bother with this? Why not just keep our systemd units or our Docker containers, if you will, around, okay? So with self-hosted Kubernetes, one of the big things that I hope to prove to you is it actually allows for bootstrapping to be simplified. When a node comes online, it actually only needs a few pieces of detail. Specifically, how do I talk to the API server? It can join as either a master node or a worker node and do its work. It's going to simplify cluster management. This is one of the heartaches of Kubernetes sometimes, right? You have this massive distributed system. When you need to go from 1.5.0 to 1.5.2, what does that process look like? What do you need to tear down and pull back up? And I'll show you how this model can make that quite simple. And then finally, and if I could just, without ruining this wall, highlight this line right here. This is really the crux of it, right? You have so much operational expertise and so many benefits that you get for free from using Kubernetes. Why don't we use those same benefits and use that same operational expertise to manage Kubernetes itself, rather than just having a completely separate method for managing the control plane components? And the example I'm going to show you right now is scaling. So let's come back to this right here. Right now, I've got an API server, I've got a controller manager, and a kube scheduler. So those of you who can read this pretty easily, how many controller manager and scheduler instances do I have currently in my cluster? One, you got it. So technically, I don't have an HA control plane at the moment, right? So how would we go about setting up an HA control plane? Well, keeping in mind that these are effectively Kubernetes deployments. So if I come inside of here, and I'm just going to do a watch in my top window here for the deployments. So deploy in the kube system. We'll see if it's reasonable to watch here. Okay, not too bad. And then in my bottom window here, I'll actually start modifying the cluster, right? So what I want to do here is, let's say I want to scale my scheduler up to 2 schedulers. That way I've got some level of high resiliency. So I can come in here and say kubectl. I want you to do the scale operation for the deployment of kube scheduler, okay? And I want to specify replicas of 2. So I want to have an HA plane where I've got 2 schedulers. And in this case, it'll be namespace kube system inside of here. So as I hit enter here, this is going to scale up my kube scheduler just like it would any other deployment inside of Kubernetes. So now you can see my scheduler is highly available. Now what this means in an HA control plane is, once again, are both of the schedulers running at the same time, or is it an active-passive? Active-passive, right? So one scheduler, one pod, should effectively be the active one doing the scheduling, and the other one should just be kind of hanging out. So let me go ahead and test this theory out. So let's say I want to see what my schedulers are doing. Well, we can go inside of here and once again do a watch. This time let's do pods, which will be a little bit more information, but we'll check out what's going on in the kube system. All right, and make this just a tad smaller here. Okay, so sorry for those in the back. I'll highlight what I'm pointing out here. But effectively, if we look in here, we can see the scheduler is running on 2 pods, right? So if I come down to my bottom window and I say kubectl, give me the logs for the pod, or actually I can just put the pod right in here, for this pod, right? Inside of namespace kube system. This first pod that I'm going to be logging out here is actually the active scheduler, right, inside of my HA control plane now. And you can see how it's made like logs saying, hey, I scheduled this thing, I did this piece of work, right? And being an HA control plane, the scheduler now should be kind of in the passive mode, the one that realizes, hey, J9CJM has a lockout. It is the active scheduler, and I'm just hanging out in case it were to die. So if I run the same command for the logs inside of the, I'll just paste it in, make sure I don't make a typo here, for the 645XJ, all right, this should effectively have a bunch of logs saying, lock is held by kube system J9CJM, right? So just like that, we took our non-HA control plane, scaled it out, and made it HA. And these schedulers in this case are running in their active-passive mode. So if I lose one, the other one's going to pick up right where the other one left off, okay? And again, I won't bother showing you the logs on this one, but I am going to scale out the controller manager too, just to make sure we've got a truly HA plane, if you will, here. So let's do scale one more time. So scale, and this time we'll do the cube controller manager. All right, and then in a moment here, if my top window is still watching here, I know it's kind of tiny, you should see the controller manager duplicate, in which we'll then have 2 pods running this controller manager. So now we've gone from a single plane, or a non-HA plane, to an HA plane by scaling these out, all right? Now the API server is a bit of a different beast because it's a daemon set, and we'll talk a bit about that in a moment. But now that you've seen kind of the scaling and how we've effectively created an HA control plane, do I have any questions so far on what we've done? Yes, please. That's right. Oh, yeah. Yeah, great. So the comment more so, and if there's a question in there, let me know, was, so in the case of the scheduler and the controller manager, which are deployments, they're active passive based on the nature of how Kubernetes does HA. And you're totally right in your other point, which is the API server, and I'll show you how to scale that out in a moment, that is going to be active, 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 because it can sit behind a load balancer or a service. Yes. In the scale command, you would not specify it because the actual unit itself, in this case, the controller manager, understands what it needs to do as far as active passive goes, if that helps out. Yeah. Great question. Yeah. So effectively, the question is, when you're scaling, is there any type of magic or specification you need to do to make these behaviors occur? And this is effectively what these components will do just by the nature of Kubernetes. Great question. Anything else so far? Awesome. Okay. So let's talk a little bit about bootstrapping and how that relates to the API server in a moment as well. So effectively, when you're in the self-hosted model, what you need to be doing is you need to have a couple components, right? You need to have a kubelet on your host, so that's the first thing. You're going to have a container runtime. All of us running Kubernetes, I'm sure, are using Docker as our container runtime, so you're going to need Docker, okay? Rocket as well if you're using Rocket for any pieces. And then a kube config, which would basically have enough information inside of it to tell the kubelet, here's how I talk to you, here's how I reach out to the API server, okay? And as long as you have this information in every node, whether it's a master node or a worker node, it will be able to join the cluster and do its job. So what this translates to us as operators, the one kind of non-Kubernetes thing we need to do is we need to hop on whatever our Linux machine is, and we need to make sure that we hop into our package manager and get these components, the kubelet, the runtime engine, and so on. Plug for container Linux, we have the runtime engine and the kubelet already inside of there. But if you do not, if you're hopping into Ubuntu or whatever it is, you can really use any distro you want, Red Hat, and you can just make sure you have these components on your host. And when it starts up, it is effectively going to join into the cluster in the self-hosted model, okay? Now, the big difference here for your master nodes is when you start these up, since they are a lot more important than a non-self-hosted cluster, you want to make sure you can flag them and say, hey, you're part of the control plane, if you will. So when we start up our master workloads, we can obviously label them using kubectl, our master nodes. But when we have the bootstrapping information, like say in a systemd unit or just a Docker container that we're passing flags to, we want to be able to go in and say, I am a master node, okay? That way when I join, I know things like the API server belong on me because I am part of this master node. And that's the example that I'll give you here right now. So in our case, this is an Amazon cluster that I'm running. So what I'll go ahead and do inside of Amazon here is I'm going to go into the auto scaling groups. And those of you who are not as familiar with Amazon, just think of this as a way to set thresholds for when you should spin up new boxes, new machines, right? So if I come inside of here and I'm in the JR Meetup auto scaling group, yep, I'm going to come inside of here and edit it. And I'm going to bring my desired size of nodes for controllers up to 2 for all these different fields just to make it simple. So effectively, this is a very manual way of saying, hey, Amazon, I want 2 controllers in this case. So I'll save it up. Amazon will say, hey, Josh, I'm working on it. I'm getting this next instance bootstrapped. Now, the auto-scale controller, and just to maybe kind of show you one of these controller nodes real quick, that'll probably be the easiest here. So if I go into my existing controller node through SSH, so let's see here, controller, JR Meetup controller, yep. Grab this IP real quick. So I'm just going to SSH into this real quick to give you a quick preview. SSH, use my key. Okay, and this is a CoreOS Linux node in this case, but it can be any distribution you want. All right, so I'm inside of the existing controller, and looking inside of the existing controller, how we have this set up in CoreOS is we actually run the kubelet as a systemd unit, and we have that systemd unit launch a privileged rocket pod. But again, your mixture could be different. You could just have the kubelet running out of a Docker container, out of a pure systemd unit, and so on. There's a lot of options available to you. I just SSH'd into the controller node that has the containers on it. You got it. I do not have a separate container that's running the SSH session. Yes, good call out. So if I do come in here and say systemctl edit kubelet, so this is for, I don't know how familiar you are with systemd, but this is basically me saying, give me the systemd unit that expresses how to start the kubelet. I'm going to go inside of here, and inside of this configuration that is slightly highlighted, believe it or not, is the flags that I'd pass into my kubelet, that agent that runs. In particular, you'll notice I have node label set to master, right? So these controller nodes have this flag turned on such that when they join the cluster, we should have daemon sets that are specified to only run on the master nodes run on them. The API server is an example of that, okay? So again, if I pop back out here, and this time I'm going to leave my node, so I'm back on my host machine here, okay? If I go into my, let's do the API server real quick. So if I edit the deployment for the Kube API server inside of Kube system in this case. Okay, Kube system. All right, this is edit Kube API server. Oops, edit deploy. Let's see here. Deployments extension, error not found server, Kube system. Let's see, what do I got going on here? Let's get deployments real quick. Make sure I'm not missing anything. Kube, get deploy, namespace, Kube system. Okay. Oh, it's a daemon set. That's why, as I just called out. So daemon set, Kube API server. Okay. So I'll bring open the edit here just so it's a bit easier to see. So this is effectively the API server. And like I had mentioned, being self-hosted, the API server is really just a manifest like anything else. And being a manifest, it has information about the etcd servers it should be contacting, whether it's a privilege, whether it should run as privileged or not, a bunch of different common information about the API server. In particular, if we look inside of the node selector in the manifest, it's set up so that I run as a daemon set, but I only put myself on nodes where master is set to true. And that's what you just saw in the kubelet on the host. It says master is true, okay? So what does this all mean as far as our HA control plane goes? Well, effectively, if we go back to Amazon for just a moment and refresh, and we look inside of the controller, you can see I've now got 2 controller nodes running. So just by this second controller node running in my Kubernetes cluster, I should now have 2 API servers active based on how that daemon set is configured. So if we come in here once again and we look into our watch here, try to clean it up, it's a bit of a delay, there we go. For the Kube system, oops. Refresh, there we go. Okay, so now you can see we have 2 API servers running. So now you've achieved an HA control plane. You've got 2 controller nodes running, 2 physical hosts that are considered controllers or masters. Those are each running an API server. We've got a controller manager and a scheduler. And all that we did was use native Kubernetes scaling commands and daemon set features to achieve this highly available control plane, okay? All right, pause there for a sec. Questions so far? Anything you can think of? Yes. Yes, great question. So as far as like the scheduler and controller manager goes, setting up settings such that they ensure I can't remember exactly what the flag is in Kubernetes, but say again? But these guys are actually running as deployments. So you bring up a good point, which is the question of how do I guarantee that they don't run on the same node? So you can actually tell the scheduler in Kubernetes one of two things: never run on the same node, or you could even express, I prefer you to not run on the same node, but in a worst case scenario, run on that node anyways. Yeah, so great point and question. Yes, good. Please. Yeah, no, it's a totally valid point. It's a totally valid point. So as far as, and honestly, I'm not even sure with how we set it up by default. We might even have that setting already there, but nonetheless, 2 controllers running on the same node theoretically is better than just one, because it's possible that one container could die for some weird reason, like it got a weird signal from the operating system or whatever. But it doesn't buy you much, right? Because what you're really worried about is your host failing, right? Exactly, single point of failure. So spreading those out is totally logical and totally possible, just like you can in any Kubernetes deployment. You can tell any of your deployments, I prefer the replicas of myself to prefer being scheduled on different hosts. Yeah, great question. So is there any reason that we don't run the scheduler and the controller as a daemon set? I think it's really a flexibility of scaling thing. It gives us just a little bit more flexibility, but there are not really, at least not off the top of my head, technical reasons why that wouldn't be possible. So yes, please. Yes. Yeah, totally. So now so the question is, how do you kind of provide segregation for 2 clients that are communicating with this overall cluster? Do you mean from a pod level of apps being deployed in inter-pod communication, or do you mean like from a kubectl operator level, or both? Yes. So I guess, so is the question, how would these be able to schedule across those CIDRs? Or I'm not sure if I'm following exactly what you're. Oh, sure. Yeah, so. Totally. Yeah, so short answer to that, and how you can kind of, let's wrap it up as provide network level configuration, let's say, right? For example, with Flannel, and if you were to plug Calico in and things of that nature, you can do a lot of that by just expressing config maps that these guys will then use and be able to inject on the hosts as needed if the kubelet needs that information as well. And a lot of the stuff too, you could just provide in the flags for the deployments as well. So that capability is more and more moving into standard Kubernetes config maps and secrets, and less on like host file configs that you'd have to express and stuff like that. Yeah, so like the CIDR that the API server is going to look at and things like that, for example, that's actually going to be in the manifest for the API server at this given point. And then I guess to a degree you can consider the config maps hard coded in a way too, right? That things like Flannel and stuff will look at. Yeah. Yeah, please. Yes, actually, if I could punt that for a second, because I have a self-hosted etcd piece that I want to talk about, if that's cool. Okay, yeah, so if you're curious about where the heck is etcd in this equation, first off, note that I actually have etcd running on separate hosts. So the one piece of this equation that is currently not self-hosted is etcd. But I will try to sell you on why etcd self-hosted actually makes sense. And some of you might disagree with me or agree with me. Nonetheless, you have both options, okay? But for right now, etcd is running outside of my Kubernetes cluster. Okay, great questions, everyone. Let's dive a tad deeper here, okay? So one of the big benefits here is simplifying Kubernetes lifecycle management. And what do I mean by lifecycle management? Well, a lot of this stuff is really convenient, or a lot of the Kubernetes features are really convenient for managing our own software. And if we're running Kubernetes clusters, we probably generally agree, plus or minus a couple things we don't like, the Kubernetes does a really good job of handling replicas, scheduling, updates, all that good stuff. So ideally, we want to minimize writing external software that manages Kubernetes, and that's really where the self-hosted piece kind of comes in, because we want our solutions to be as portable as possible, right? We want to effectively not have something that's super fragile and specialized, but something that's more Kubernetes focused and can span even cloud providers and data centers. Why can't your bare metal deployments be identical to the way in which you do your deployments inside of AWS and Azure and so on? So again, our tools ideally would stand on the shoulders of Kubernetes itself. So a great example is updates. So I think 1.6 is in beta right now. Is that right? Head nods if anybody knows. Okay. Anyway, so 1.6 is getting closer and closer to being out with the code freeze and so on. And at some point, we're probably going to want to upgrade because who knows? Maybe there's just new features in 1.6, or maybe there's a legit vulnerability that we need to take care of. So updating is something we always need to be able to do quickly and easily. So just like any other deployment in Kubernetes, we could effectively have manifests that express the updates or the changes we want to make to each of these components to update them. So if we want to bring the scheduler up and the controller up a version or a dot version, we can do that by effectively editing these files. So an example that I can give you here inside of this cluster is, let me watch these in the top actually. So is the controller manager as an example. So I'm going to go into the controller manager. So kubectl edit. In this case, it's a deployment. So deployment kube controller manager. All right. Namespace is kube system. Okay. So again, the controller manager, like everything else, is a manifest. And if we go inside of here and look for the 1.5.2, which I believe it's running, okay. So here is my image version for my controller manager. Now, if I go into, and this is, by the way, I don't know if you guys are familiar with Hypercube. It's just like all the control plane components in a single binary that you can run. So effectively, we're using Hypercube to run the controller manager. Now, let's say I want to go from 1.5.2 to 1.5.3. Since this is hosted in Kubernetes, I have the flexibility to go over to where I host my different versions and find the version I want. In this case, 1.5.3. Okay. Grab this version or image. And I can change this in the manifest. And a great thing about this, I'm going to save it and kind of show you it updating here, is I'll save the manifest and quit. I'll go back to my watch here, and because this manifest, like many deployments, is set to be a rolling update, it's going to take care of bouncing one controller manager out, updating it, replacing it with a new controller manager, and then going down to the next controller manager and doing the same thing, such that we never are in a state where we've completely lost our controller managers. And again, Kubernetes benefits, right? What if something goes horrifically wrong, right? How nice is it to be able to roll back with the same Kubernetes tooling you're used to? And I'll show you some disaster recovery scenarios in a moment. But at this point, using rolling updates in Kubernetes, our controller manager has just been upgraded to 1.5.3 from 1.5.2. Now, I want to keep my controller components on the same level. So just to be safe here, I'm also going to go in and do the same thing for the scheduler as well. So kube scheduler, oh, typo. Schedule array, yes. Good stuff, French, yep. So we come down inside of here, we find that exact same version. We go in, we grab the new version, and we save it up. And once again, if you watch closely here, and you won't be able to see it because it's cut off, once watch refreshes, possibly you'll see it. The scheduler should go through the same rolling update. Come on, watch. There we go, watch. Oh, and watch was too slow for Kubernetes. So 28 seconds, 33 seconds, you can see that these had just started. We went through the same process. So effectively, we've set up an HA control plane, and we've just updated Kubernetes versions through rolling updates. Now, let me come to that in just a quick point, and then I'm going to come to that. The API server, which if I did it right now, would be the exact same process, but there's one feature that daemon sets currently don't have, rolling updates. So we'd have to either write some piece of code or go in and update the daemon set and then kill these pods, right? There is a, I think I have it even a link in the slide somewhere, where we're getting daemon sets to have rolling updates in upstream, so it can do the same thing that these controller managers and schedulers do as well. Okay, sorry about that. Go ahead.
That's okay.
Yeah. That is correct. So
Does CoreOS have, is it part of CoreOS capability to sort of, I would say, atomic upgrades?
Sure.
Ability to roll back and
Yes. Right. So the question is around, this update system, is it part of Kubernetes, and is this kind of related to what CoreOS from a Linux standpoint, an operating system standpoint, does? So the first point, yeah, this is totally just normal Kubernetes management, and we're just simply, like I mentioned in the slide, standing on the shoulders of Kubernetes. We're taking advantage of its already existing rolling update and rollback systems to make this happen. Now, you actually hit on a huge parallel that I don't really talk about in these slides, but is important. One of the big things with our Linux distribution that we're focused on is that when things like dirty cow root escalation vulnerabilities come out, or some other Linux like evil lamb or whatever the next one's going to be called, right? We need to be able to patch those, because those are extremely serious. If you have root escalation opportunities in your operating system, what could happen? It could be D-Day, right? So effectively, in our operating system, we've been focused on, this is before CoreOS even got into the Kubernetes world, on having an operating system that follows kind of a similar model, where we effectively just update things as stuff comes out. Now, this is a little bit more manual. What we do with our enterprise Kubernetes solution, just to plug it and be a salesperson for a moment, Tectonic, the enterprise version, does all of this for you. So when Kubernetes updates, when features come out and so on, you have ways to set up different policies and whatnot, such that Kubernetes could just be updating. And ideally, at least at CoreOS, we think Kubernetes is so great that we almost like parts of its management like this to just fade into the background, and you just benefit from the actual deployment and stuff like that. Hopefully that answers it. Cool. Yeah. All right. So is it okay if I go a little bit over since our second guest? Okay, is that cool? All right. Cool. So continuing on for a moment, let's see here. Yes, slides. Okay. So we've updated everything. And okay, so one of our big focuses at CoreOS is keeping everybody secure. And keeping things up to date is extremely important, because we never know when certain vulnerabilities are going to come out, whether that's low in the Linux level or higher up in the Kubernetes level. So effectively, this gives us a way to stream, if you will, these upstream Kubernetes pieces directly into our control plane. And again, just to kind of really harp on this point, take your expertise around management of software in Kubernetes and apply that to the control plane itself. All right, so let's talk about how exactly this occurs. Now, here's the tricky part to setting up a self-hosted cluster. In order for a self-hosted cluster to start, we need an initial control plane to bootstrap that self-hosted cluster. So effectively, if you've ever seen like the talk that Aaron Levy gets, in fact, I stole some of his slides for this. He's one of our engineers who works on this stuff. He refers to it as the chicken and the egg problem, and it very much is, right? Because in order to set up the self-hosted Kubernetes cluster, we do need an original Kubernetes cluster. So this is where the tool Bootkube comes into play. So Bootkube is a Kubernetes incubator project that we work on and a couple other contributors work on that effectively acts as a temporary control plane, so that we have just enough pieces in place such that we can bootstrap our self-hosted control plane. And again, this temporary control plane is totally ephemeral. Once Bootkube comes up and gets everything set up, we expect it to die and never come back. So, oh yeah, and I'll mention the GitHub link too. If any of you are interested in checking out Bootkube, this is what we're pushing up to the Kubernetes Incubator project. It's literally called Bootkube, so feel free to check it out. Now, I'm going to show you both in a live demo and in some graphics exactly how Bootkube works, in case any of you want to go home and try out some of this self-hosted stuff. Because after we work in Kubernetes all day, obviously we go home and use Kubernetes all night, right? So, okay, so we get ourselves set up here, and we've got our kubelet and our etcd. Now, again, just to clarify, those on the video as well, I'll dive into this more, I promise. etcd is currently outside of Kubernetes. Let's assume that's the case. It's being hosted elsewhere, your data store. The kubelet, the agent, starts up on the host. Now, the kubelet just starts kind of going, all right, I'm up. Where are you, API server? Where are you, API server? And just goes through this constant loop of where the heck are you? So let me show you exactly that here. So if I go into an SSH session, so docs, meetup, IP, okay. So I am going to log into a node. This is a completely different node, not part of my cluster. This is a bootstrapped cluster that or node that I'm about to show you, okay? So this node that I am in is one that the kubelet is up and just going, how do I talk to the API server? Somebody help me. How do I talk to the API server? And to show you that, if I run, not resize, but if I run journalctl, okay, there we go. So this is printing out the logs of the kubelet. Now, it's kind of obnoxious and small, but if you look closely at these URLs, suffice to say that the kubelet is just kind of going, API server, where are you? Where are you? I'm failing to reach to the API server. Here is our chicken and the egg situation. How do we tell the kubelet, hey, kubelet, launch the API server, launch the scheduler, launch the controller manager when it doesn't have the API server to initially talk to? This is where Bootkube comes in. So what Bootkube is going to do is be this very simple binary that we can bootstrap such that the kubelet will have an API server to talk to. So once Bootkube starts up, the API server talks to the data store etcd and understands exactly what's going on inside of the cluster. The scheduler and controller manager are, of course, talking to the API server as they do to understand what work they need to do. Now, at this point, the kubelet is going to be able to start setting things up. So let's look at what that means. If we go back into this cluster here, I'm going to keep our very verbose friend up top there, okay? And I'm going to SSH into that same node again. So if I SSH in here, all right. Okay. Now, inside of here, if I go into opt bootkube, this is where I put my bootkube assets, and I look inside of the assets directory for Bootkube. One of the key files in here is, let's suffice to say for now, this is the Bootkube binary I was telling you about, okay, that launches the temporary control plane for Kubernetes. Now, along with Bootkube, there's a stack of manifests, and you could probably imagine what's inside of this group of manifests. If we look inside, this manifest contains all of the YAMLs, or descriptors, for our API server, our controller manager. We've got Flannel in here, kubedns, so on and so forth, okay? So once Bootkube starts, it's going to be able to apply these pieces. So that's pretty much exactly what we'll do here. Let me just make sure I am in different nodes. Okay, I should make sure that I don't run Bootkube in my good cluster. So I'm going to go ahead and get into my docs real quick for the Meetup. Okay, and I'll cat that IP again, make sure I'm in the right spot. Yeah, I was not in the right spot. Okay. And I'm basically going to run Bootkube in the bottom here, just so we can kind of see this initial bootstrapping happen. So go in for opt Bootkube, yes, thank you, and assets Bootkube start. Okay, now Bootkube is also insanely verbose. So you'll get to see Bootkube start, but again, keeping in mind that Bootkube is starting the temporary control plane. And once Bootkube gets to a far enough along point where the API server is up, told you it was very verbose, the API server is going to stop saying things like could not talk. In fact, you're seeing some of this right now. It's very subtle, but you'll see things like adding node, right? It's starting to recognize on the kubelet that there's an API server it can talk to, right? Now let's actually see it somewhat visually here. So the Bootkube is up and the API server is talking to etcd. Bootkube realizes, hey, I got my API server up, I've got the kubelet up. It's time to make sure that we can deploy all of our deployments, daemon sets, services, and secrets, because that's our control plane in a Kubernetes context. So let's apply all of that and store it such that the API server and etcd are aware. Now, once those items get created inside of your Kubernetes cluster, you now have a hosted control plane. So you've got the API server, the scheduler, and the controller manager all running inside of here. Now, there's an obvious problem. Bootkube's still hanging out, and we really don't want it to anymore, right? So what we can do at this point is we can say, all right, Bootkube, you're done. When Bootkube gets torn down, the kubelet is basically going to lose network connectivity. But what's going to happen in this moment is the API server that we have running in the cluster is going to come online, and the kubelet is going to be able to talk to that API server. So kubelet kind of thinks there was like a network mishap or a blip, right? And now it's talking to the API server, and now you are officially self-hosted inside of Kubernetes. And Bootkube ideally never comes back after this. It's a done deal. So if we go back inside of this piece here, oh, good job, Bootkube. So Bootkube basically said, hey, I'm started up at this point. Here is my information around my Kubernetes cluster. I started up a 1.5.2 Kubernetes cluster, at least initially. The kubelet, for those of you who have really looked at the kubelet logs, is basically just doing some final volume mounting inside of here. And now this is a self-hosted Kubernetes cluster. That's it. We just need to have that initial communication with Bootkube to get these pieces deployed and up and running. So that is our bootstrapping process. Questions on how Bootkube bootstraps via this temporary control plane? Anything you want to ask? Yeah, so question is, are the IP that you'd address, like the API server and so on, the same? And the answer is yes. Yeah, you got it. On the same host, you got it. And keep in mind, Bootkube only has to run on one controller node initially, because once this guy lives, now all your other kubelets can talk to it via a service abstraction or IP. Exactly. And now you have the ability to scale it up just like we saw. Yes, question? Bootkube is itself a container. You got it. So you can go out and you can run it in Docker. In this case, just because we're really big fans of systemd and going through that, we just run it in a Rocket container, but you could run it in a from the Docker runtime and bootstrap, no problem. You got it. And I think in our docs, we have examples for a couple of different bare metal solutions, including like just Vagrant, if you want to just do something local and test this out. Yeah. So. Yeah, you know. Not like a true QA environment, but like just want a Kubernetes in the box. Yeah, it could work pretty well. Obviously, so the question, by the way, sorry everyone online, is could Bootkube work as kind of a quick bootstrapping testing environment? Minikube's probably a little bit more convenient, but you probably could bootstrap something that's a little bit more realistic locally and then test on that. Yeah, great question. So your question is, will the pods be on a different node than where Bootkube is running? And are you referring to these pods here? Yeah. So effectively, what's happening out of the box here, we have a couple options, but the one that I just bootstrapped a second ago is running all these pods on my same server because I'm just doing a single instance. So effectively, we can set this up such that Kubernetes will just scale these out. So you'll not have, after you bootstrap and scale it out based on how many controllers you want and so on, you can have 3 API servers, 3 schedulers, 3 controller managers, all on different nodes right out of the box. You just need to make sure that this gets scaled and doesn't just run on a single machine. Yes, great question. Yes, go ahead. Sure.
Just functionally, the kubelet, is it capable of broadcasting out and finding the different pods? Is that sort of automatic?
To a degree. So the question is the kubelet capable of kind of going out and broadcasting to find these pods and so on? Basically, it's more tuned to go out and broadcast and locate the API server.
But finds the one on Bootkube, if it does end up on a different pod, and I don't know all my nomenclature, but can it find it if the API server does end up on a different IP address?
Totally, absolutely. So the question is, if the API server ends up on a different IP address or whatnot, what we actually do out of the box, and I think this is a Bootkube thing and not just a Tectonic thing, our enterprise piece, is we actually put a Kubernetes service in front of the API server, which I don't know how familiar many of you are very familiar with services, I'm sure, but basically think of that like guaranteeing that you can always locate the API at a specific virtual IP.
It's fixed and then it's
yes. Yeah, exactly. And regardless of where that guy lands, your kubelet is going to keep communicating through that DNS record or service or whatever is kind of pointing down. Yeah. Well, yeah, I would say this. So as far as relying on the API server to solve that problem, everything has to go through the API server at some point. So if that kind of helps bring it full circle. Yeah.
So question from the internet.
Yes, please.
How when you use the controller node autoscaling group, how did they join the cluster, and how would you do that with bare metal?
Yes, great question. So if we have a controller manager or excuse me, a controller worker autoscaling group, what we're doing right now in the AWS context is in the kubelet itself, when we start the kubelet, we're passing a flag saying you should be a master, okay? And by passing that flag in AWS, that means we are using basically their user data in AWS. Have some of you use user data in AWS? Yeah, okay, cool. So what we use in the CoreOS world is we use something called ignition templates, which is a fancy way to express how you want your machine to be bootstrapped. And that will actually go in and bootstrap that. And with bare metal, for at least CoreOS Linux, or container Linux rather, we have a very similar setup with Ignition, where in bare metal, you can do the same thing such that when your machine comes online and sets up the OS through Pixie booting or whatever you've got set up in bare metal, that Ignition template can actually be injected and brought in, such that when the operating system starts, it will actually run the Ignition template and make sure that the configs are set in place. So you can basically replicate something very similar. Now, if you're not using container Linux, it'd be kind of variant based on your operating system and how you do configuration of those systems as they come online. Great question. Okay, I am pretty close to being done here. I just want to show you self-hosted etcd and then go over some disaster recovery, and that's all I've got. So again, just a reminder, the self-hosted control plane consists of our API server, which is a daemon set, the scheduler and controller manager, which are deployments, kube proxy, which is doing some abstractions with like IP tables and fancy stuff to make services work in Kubernetes. And then even like our TLS assets and service account keys can be stored as API objects through secrets and config maps. Now, another area that actually kind of beat, in my mind, kind of beat the whole Kubernetes control plane to being self-hosted is pod networking. And excuse me, you might have seen this a bit with Weave and Calico and so on. So effectively what we can do is when these guys get bootstrapped, if the kubelet knows that it should be using CNI to do networking, it will need, excuse me, some configuration files to achieve that, okay? Now, what's nice is these pods that are getting set up, like the API server and so on, can use host networking. So they can still get set up and bootstrapped. And Flannel, for example, as a daemon set can come on, and those Flannel nodes can go in and set the configuration for CNI in all of the nodes across the cluster. So what's kind of neat about this is one group that we work with a lot at CoreOS is Ticketmaster, right? And a lot of the network policy work that they need to do means that they need to do both Flannel to have a really nice network overlay over VXLAN, but they also have a lot of requirements to make sure that pods can't just talk to any other pod. So we have to plug Calico into that equation as well, creating what they call nowadays Canal, right? Calico and Flannel. So both of these are totally self-hosted. We just drop the Flannel daemon set in, we drop the Calico daemon set in, and now we've got Canal running in our cluster with network policies and full CNI overlay, right? So it's pretty nice to bring the pod networking pieces in, excuse me, as well. Okay, and now here's where etcd comes into play. Show of hands, has anyone seen our operator work by chance with like the etcd operator or Prometheus operator? Okay, just a couple. You should check them out. They're really neat. So we're doing a lot of work around operators, which is like deployments that have operational knowledge of how the deployment should happen. So think about this for etcd. Etcd, when you set up an etcd cluster, you need to understand how the etcd API works to add members to it, make sure it's resilient and so on, delete members from it and so on. So we're doing a lot of work with things like etcd operators where you can go in and you can say, hey, I want to deploy the etcd operator. And since the etcd operator has the knowledge of how to run etcd, it can make the informed decisions in your cluster of how to add and remove members. So why I bring this up now is this is something we're working on bringing into Bootkube, so that those of you who play around with self-hosted clusters will have the opportunity to possibly have etcd in that equation as well, because that was the one piece that we had sitting outside of our Kubernetes cluster. So what does this mean? Well, with the etcd operator, what we could do is we could have Bootkube start up, and Bootkube could start up with an etcd node, okay, which its API server talks to. Now, as we talk through the kubelet to the API server, we can start instantiating our own control plane inside of Kubernetes through pods. And what we'll do here is we'll actually set up the etcd operator, which again understands how to create, destroy, and so on etcd clusters. So what this means is, excuse me, the etcd operator could go out and use this Bootkube etcd as a seed node. Basically saying, all right, let's go out, let's make sure that you're known as part of the cluster, let's use you as the baseline. Then the etcd operator can add a member in so that you have an etcd node running inside of the Kubernetes cluster. Now, since the etcd operator understands how etcd works, it could add the member formally. That member will understand that it is now part of the cluster and taking part in the consensus algorithm. So it will start going through and getting all the data that it needs to be part of the etcd cluster. So what this then means is what we can do with the etcd operator is we can say, hey, go ahead and remove the Bootkube member because you don't need it anymore. And when Bootkube goes away, etcd is totally self-hosted. And just like we talked about with HA before, you now have the ability to have etcd scale to a 3-node cluster, a 5-node cluster, whatever you need, but it will scale across your environment. Now, obviously, one of the big heartburns that people would get from this is that etcd is the data store for Kubernetes. So it's like, you want me to put my data store in Kubernetes. And that concern is totally valid. But go out if you get a chance and check out some of the work that's being done on this etcd operator. Things that you can do, like set up persistent volume claims and stuff like that for disaster scenarios such that you have some form of backup, are all possible. And once again, as far as like your resiliency, you're basically in the same boat as long as etcd is spanning the nodes you want it to span. And once again, upgrading and changing things can all be done through this operator and through core Kubernetes components. You're not actually managing etcd on separate machines that Kubernetes is talking to. Okay, so we're doing some work in that space. Check out the operator. It's not there yet, but it's getting closer and closer. And if any of you, does anyone here use etcd for like service discovery outside of Kubernetes? Okay, cool. So if you do any type of like etcd work where you run an etcd cluster that is not being used for Kubernetes, being used for other stuff, because it's a really good distributed key value store, right? You can use the etcd operator for a very easy way to say, hey, Kubernetes, I need a new etcd cluster in my environment so this team can start using it to do like service discovery and can, to a degree, config management or lock management or whatever you're using etcd for. All right. And then I have one final section. Thank you all for letting me go over a bit on disaster recovery. Before I do that, etcd questions from the web or the room? Anything you want to ask? Okay, let's talk disaster recovery, and then whatever questions you might have, we'll try to field. So last but not least is, all right, Josh, my Kubernetes cluster is running in Kubernetes. What happens when stuff goes really, really bad? And that's totally valid concern, obviously. So a couple scenarios I'll take you through. What does it look like when a node fails? What does it look like when you lose all of a single control plane component, like all your schedulers? What does it look like when you power cycle a machine? And what would it mean if you just literally lost everything? Your data center goes down completely or whatever, and that's it. What do you do? All right, so the first one is the easiest one for me to answer. What happens if I lose a controller node? Well, that's the great thing about this model, and it's something we get for free with Kubernetes. If your node goes down, spin another controller node up, let the scheduler take care of redistributing the API server, the controller manager, and so on. Business as usual. As long as you're in an HA environment, if you lose a node, no big deal. And that's one of the reasons we use Kubernetes for our apps as well. Now, where it gets a little bit more complicated is, what if I have partial loss of my control plane? Okay, so you have this item in Kubernetes called a scheduler that makes informed decisions of how to schedule stuff. So what if you lost all your schedulers? When Kubernetes tries to recover your scheduler, it's going to need a scheduler to schedule your scheduler, right? There's no way around that. So this is where if you did have some weird situation where you lost all your controller managers or all your schedulers, you would need some way to still bootstrap the scheduler. And actually, you can still do this with native Kubernetes components. And that's actually something I'm going to show you, because it seems borderline impossible, but I promise you, you can. So we can go in here and basically tell Kubernetes, hey, I want to schedule a single copy pod of the scheduler, even if it's just temporary, an ephemeral scheduler, and then I'll get rid of it. I'll rip it out when I've got everything back to normal. So let's try to replicate this use case real quick. So we are inside of our cluster here. The scheduler is a little bit hard to see, so let me. I have a massive 1 pixel I can grab onto here, so bear with me as I try. Look at that. There we go. Oh, look at that. Nice. Okay. All right, so once watch updates, I think you'll see my scheduler again, but I'll get us prepared here. So the first thing that I'm going to need to do is I'm going to need to scale my scheduler down. Let's do scale again for the scheduler, down to 1. Because obviously if I kill a scheduler, Kubernetes is going to solve the problem and just schedule another scheduler. So I can't have that happen. So I am going to scale my scheduler down. These 2 lines you see right here should become 1 once the scheduler is brought down. There we go. So now we're down to 1 scheduler. So now let's go through that D-Day scenario where we actually kill this scheduler altogether. So if I come inside of here and I delete the scheduler, so this is a deployment, yep, and we call this actually, this is a pod that I want to kill, right? So if I kill the pod for this scheduler here inside of kube system, okay, this should attempt to delete my pod, which of course there is still a controller manager, replication controller that's going to try to keep this guy around. So effectively what we should see, depending on how quick Kubernetes is, yes, good, is that the scheduler is down and Kubernetes realizes via the controller manager, I'm supposed to have one of these guys running, right? But I don't because I'm saying Kubernetes, I need one, and the scheduler is nowhere to be found. We have no idea where we should place this pod. So let's try to solve this. So effectively what we can do here is we could actually grab the scheduler's manifest and utilize it to kind of bootstrap almost like a static single-use pod in the cluster just for temporary use to get us back up and running. And to show you this as well with the scheduler, let me go ahead and just run an Nginx as well, just to show you. So I'm going to bring 2 Nginx instances into this equation. So 2 load balancers, Nginx, whatever, are going to get deployed. And they should follow a similar model with the scheduler where Kubernetes knows you want 2 Nginx pods, but I don't know where to schedule them. Oh, yes, good call. I was looking for kube there. So down here, 0 out of 1, pending. We're stuck. Our scheduler is gone. All right, so let's try and solve it. Now, what we can do here, once again, and I'm just going to go into my, my docs here. I've got a sample file. Is I am going to take the deployment manifest out of Kubernetes for the scheduler itself. So I'm basically going to say kubectl, excuse me, get the deployment for our kube scheduler. We'll set this out in YAML. This will be part of the namespace kube system. Okay, and I'm going to save this in a file called deploy.yaml. You see an error? No? Okay. All right, so if that whole line makes sense, again, saying give me the deployment configuration in YAML and store it in this file, we will give that a shot. And if we open up deploy.yaml, there we go. All right, so this is the manifest for our scheduler, okay? Now, inside of the manifest for our scheduler, we've, of course, got a containers section where we express what containers should run inside of this pod, okay? So what I'm going to do here is I've actually got another file that I'm just going to bring up called pod. And this is just the starting manifest of just a pod, because I don't want to rely on the scheduler or the controller manager in this case. I basically just want to say, put this pod on the system, okay? So what I'm going to do here is I'm actually going to grab the spec for the container, and I'm going to put that inside of this here so that we've got the container spec in. All right, and my deployment's done, so I'll just show you this so it's a bit easier to see. This is my one-use pod, my save me pod, if you will. So I'm going to go up here and say the name will be save me scheduler, okay? And hopefully it will do just that. And inside of the spec, we're actually going to provide a node name. So we can say, hey, just go on this node. I don't want you to worry about anything else pod. Just get on this node and start as soon as you can. So we'll do the node name. And inside of the node name here, I need to just figure out what node I want this to land on, right? So I'm going to do a quick kubectl get nodes. And if this loads okay, I've got 4 nodes to choose from. It looks like our most recent one is the 41-minute one from earlier. So let's grab that. And we'll put in the node name right here. So now we will go ahead and hopefully get ourselves back up and running with, again, notice the version's still updated, 1.5.3 version of the scheduler. So I'll save this up. Okay, come back in. Now, what I'll do here is apply this manifest so that it can create inside of here. So we'll do pod.yaml. And barring any typos, fingers crossed, this pod should bring our system back up and save us. So we'll apply. And, okay, so far so good. Let's see if the save me pod shows up inside of here. All right, there's our save me scheduler. It's running. And if all goes well, this scheduler will eventually help the scheduler start back up. And then that guy will be able to schedule things like Nginx and so on in a moment here. You got it. Yes, it was able to run because it had the node directly specified And yeah, it was direct pod config. You got it. No RS, nothing like that. We're saved. Wow, awesome. Yeah, good stuff. Thank you. So we've averted from absolute disaster. Good news. And obviously, we're good operators, so there's probably two things we want to realize. One, we don't want to tell our boss that we brought ourselves down to one scheduler. So let's bring that guy back up to 3 this time, because we really learned our lesson on this one. And then once all is said and done, we're going to bring the save me sketch out, because we don't need that guy hanging around. Again, we want everything managed by Kubernetes. So let's go back in and let's delete. Sometimes reverse search is not a good idea. Okay, so let's delete that manifest, which I still have here. So delete that, and you probably won't see it because it'll pop out of the bottom here, but the save me pod is now gone as well. I'll just zoom in for the heck of it, I guess. Save me pod should now be gone, and we're back with an HA control plane running 3, which is pretty awesome. We have ways to get out of those sticky situations, essentially. All right. 2 more slides, and then open the floor for questions. So what if you power cycle the entire control plane? This is something that we're trying to make more and more clean. So if you were to effectively power cycle your entire control plane, lose all your API servers and all that good stuff, we've actually done some work to implement a checkpointer inside of Bootkube. So the checkpointer is a user space checkpointer that is ideally going to say, oh, I'm coming up from this disaster scenario. Let me bring back up this last checkpoint of user space. So theoretically, if you brought yourself down, brought yourself back up, your API server would come back up, right? Because that's the key thing. You just got to have the API server back up and running. Also, you can tell how old this issue is. It's number 489 in the Kubernetes project. There has been work and talk for a long time around pod checkpointing in general, which I think would bring a lot of benefits to being able to have some level of resiliency through cycles and stuff like that. But it is a challenging problem to solve. So how we do it right now, you might have even seen, I think I have them running. Yeah, they're up here. The checkpointer guys that are running on my control plane, so they're taking checkpoints of the user space so that if I come back up, the API server will come back up respectively. And then the last scenario is permanent loss of the control plane. So like, say your boxes that you run your system on don't exist in the world for whatever reason any longer, right? Well, first thing, hopefully you've got an etcd backup. If you don't have an etcd backup, then that's a whole other problem. So if you've lost all state, it's over potentially. But if we do have an etcd backup, this is something we're still trying to make a really clean solution for. But we are effectively in a similar situation with node bootstrapping if you think about it. If you had an etcd backup, if we could just go on a controller node and run Bootkube again, you'd be back up and running. Your cluster would be live again. Because you just need that API server that the kubelet can initially communicate with and bring those pieces back up. But we would like it to be cleaner and more elegant. So ideally, there'd be some type of tool, like a binary, maybe like a static pod feature, maybe even a fancier and more elegant Bootkube that could just handle this kind of stuff. So ideally, recovery once etcd and API server are back up through whatever that tooling is would mean that you're back in business, because once you've got etcd in your API server, everything else can start bootstrapping and get set up just like that. So disaster recovery, while it might be scary thinking about running your Kubernetes cluster in Kubernetes, hopefully this identifies how there's an insane amount of benefits to the maintenance of Kubernetes, and also how we're pretty darn close to having great stories around all the disaster recovery scenarios as well. And again, just to reiterate, CoreOS is a very open source focused company. We do all this work in the Kubernetes incubator for Bootkube. If you have opinions on some of the stuff you saw in this talk, things that you'd like to suggest, please hop into GitHub and voice your opinion, because we really want this to be something that we look back on a couple years from now and go, yeah, this is the way that we run Kubernetes from a control plane standpoint, right? Or at least if it's not the way, at least one of the more preferred ways for a lot of companies, so that they can tell their operators, oh, you have operational experience with Kubernetes? Well, not only do you know how to handle the CI pipeline and the app deployments and all that stuff, you actually know how to run Kubernetes itself, which is a pretty powerful message, as you could probably imagine. So there are some to-dos as well. I mentioned some of these. Pod checkpointing would be an ideal feature to eventually flesh out at some point, so we don't just have some special snowflake checkpointing for the user space. Daemon set rolling updates, getting these into upstream. I think we're maybe close. I can't wait for that, because then when you bounce your API server, you can actually have the API server do rolling updates, and there's a lot of daemon sets that would benefit from rolling updates. Self-hosted etcd, again, this is via the etcd controller, is something that we're, etcd operator, sorry, that we're working on. And then, again, building a simple disaster recovery tool. So I showed you some ways that we can get out of disaster recovery, and they're relatively elegant, but if we could have that happen for us, then the story of self-hosted becomes way more powerful, right? So that is really our next and final step. And with that, I want to say two things. Thank you so much. If you're interested in checking this stuff out, check out Bootkube. If you want to see an enterprise version of this, our Tectonic platform gives you 10 nodes for free. So if you want to play around with it and just see what Tectonic is in this model, please do. And also, we're hiring, so if anybody's interested, please come talk to me. We're building out a services organization right now that is kind of distributed. So yeah, let me know. And thanks so much for listening. I really appreciate it.
Yeah. Thanks for walking us through Kubernetes-ception.
Totally, yes.
It was nice to see recovery from disaster scenarios too. So
totally.
You get the it all comes up and it's working, and then it's hand wavy from that point.
And then what do you do? Exactly. Yeah. Totally.
Any questions for Josh? Since we have a little extra time. No questions. Hey Matt, do you want to talk about DevOps Days Rockies coming up?
Sweet.
So yeah, DevOps Days Rockies. We have our yearly conference. This is the third year in a row that we'll be doing it. Coming up April 10th and 11th. I put a code up on the board up there for 25% off. I think that brings the ticket price down to $90. It's a Monday and Tuesday. It's always a really great time. So I think I've seen a few of you there before. So hopefully we'll see you there again.
Cool. Feel free to stick around and chat with fellow Kubernetes users of various veteran status. Josh, I think that was the most technical presentation we've had here for a while. That was really good. But if you... Yes. Cool. But other than that, I mean, it's getting kind of crazy out there, a little slick, so stay safe when you go home. So, see you next time.